object gliding with purpose, until it struck high-voltage power lines and dropped to the ground.
So, the orb didn't explode, didn't hum, didn't glow, but the silence never felt natural. When researchers scanned its interior, they didn't find emptiness. They found structure, layers, symmetry that didn't belong. It looked dormant. It wasn't. Then came a pulse.
It's certainly real. It's using an energy field, a type of anti-gravity effect.
Not loud, not dramatic, but precise enough to raise alarms and strange enough to shift the entire investigation. Join us as we track the signal and the silence that may have just ended. The fall of the Buga sphere. On March 2nd, 2025, the city of Buga in Colombia's Valle del Cauca woke up to an event that would hijack global attention. Residents first noticed a metallic orb in the late afternoon, reflecting sunlight as it traced a jagged stop-start path over the tree line. It didn't behave like a drifting balloon or a steady drone. Witnesses described abrupt zigzags, quick accelerations, and sudden stalls that made it hard to track. The erratic motion created an uneasy silence across the neighborhood. People filmed, pointed, shouted, and then ducked when the object began to lose altitude. The orb came down in a wooded area on the edge of town. The impact was muted. No explosion and fireball, just a thud and a shiver through the ground that nearby residents felt in their feet. When a handful of onlookers pushed through the brush, they found the object partially embedded in soft soil. It looked like a polished metal sphere large enough to cradle like a beach ball. There were no visible seams or welds, no screws, hatches, nothing that suggested conventional fabrication. It was unnervingly flawless, as if machined from a single piece or formed in a mold so perfect that even the idea of a mold felt wrong. Within hours, new details pushed the scene from odd to unsettling. The leaves browned and curled around the shallow crater. Small plants near the edge of the impact zone went limp and then died. The effect wasn't uniform. Some vegetation remained untouched, but the patchwork of damage was enough to trigger talk of radiation or chemical contamination. Word spread fast across local WhatsApp groups and then broader social platforms. Videos of the descent and still images of the object's reflective surface ricocheted through timelines in Spanish and English, attached to captions that jumped from breathless to alarmed. Local authorities taped off the area, moved bystanders back, and called in technicians with radiation meters and thermal cameras. Early checks didn't show danger levels, but the team kept a perimeter anyway. A small crane and a padded sling were arranged to lift the object intact. The priority was straightforward: don't scratch it, drop it, and overheat it. Document everything. The operation took place under phone flashlights and a few bright work lamps, watched by residents who refused to go home. When the sphere was freed from the soil and hoisted onto a steel cart, its surface looked untouched by the crash. No dent, scuff, only a thin dusting of dirt that wiped away on a gloved finger. By nightfall, a convoy rolled the object to a secure facility for storage and documentation. Chain of custody logs began: names, times, photos. The team created a baseline: ambient temperature, weight on a calibrated scale, and basic magnet and conductivity tests that wouldn't risk damaging the surface. Every step drew a crowd online. The clip of the orb sliding onto a padded table became the most viewed video in Colombia by morning. What the town had, at minimum, was a mystery. A clean metallic sphere with no obvious manufacturing marks had dropped from the sky after an aerial performance that didn't line up with common drones or hobbycraft. A patch of nearby plants had died, though not all. People argued about what that meant.
Initial scientific findings surrounding the object now known as the Buga sphere.
An exotic battery? A heat effect? A pressure wave? The truth was simple and unsatisfying. No one knew. The object left Buga with more questions than answers. It also left a mood, a mix of pride, anxiety, and anticipation. Pride, because something rare had chosen their sky. Anxiety, because it might be dangerous. Anticipation, because everyone sensed a story was beginning. The sphere's arrival was not dramatic in a Hollywood way, but it landed with the kind of quiet that rearranges a room. Buga went to sleep wondering what, exactly, they had brought indoors. Unscripted architecture. When the crate was opened in a controlled lab, the first rule was caution. No power tools, without cutting, and heat. The team began with non-destructive imaging, utilizing X-rays at various angles, to create a layered picture of the orb's interior. The results were the first real shock. The sphere wasn't hollow, it was structured. Images showed 3 concentric shells, each appearing metallic but with different densities. Between these shells sat small, perfectly spherical inclusions, microspheres, in the lab notes, arranged with a symmetry that didn't look accidental. One set of scans counted 9 microspheres. A later, higher resolution pass reported 18. The discrepancy became a debate about resolution, contrast thresholds, and whether some inclusions overlapped in projection. What no one argued about was intent. The placement was too clean to be random. At the core, imaging hinted at a denser, roughly disc-shaped form, what observers casually called a chip. Faint, thread-thin pathways seemed to radiate from it toward the inner shell, branching like a skeletal network. On higher energy shots, several of those pathways brightened the way glass or fiber optics can under specific exposure, suggesting channels that might move light or signal rather than carry current the way copper does. A separate visual survey cataloged faint markings on the exterior. Shallow lines and symbols so subtle they were nearly invisible without raked light. They weren't scratches from the fall. Their orientation and repetition implied they had been placed there on purpose. Whether they were decorative, functional, or simple noise on the surface, no one could say, but technicians traced them anyway and stored vector files alongside the radiographs. The geometry inside raised practical questions. If the microspheres were cavities, what were they tuned to do? Resonance requires scale and material properties. Helmholtz cavities can amplify and filter. Microwave cavities can trap fields. Acoustic lattices can shape vibration. The sizes here, if the scans were accurate, suggested a design to interact with some band of energy or motion, but the band was guesswork without invasive testing. The lab was stuck with unknown interaction volume in the notes. Researcher José Luis Velázquez was the first to go on record after reviewing the full set of images. He called it a very rare piece, adding plainly that he'd never seen a piece like this. That quote traveled because it was careful. It didn't say alien, it didn't say hoax, it said unfamiliar in a field where unfamiliar usually resolves into something conventional once you've taken it apart. Here, taking it apart wasn't on the table. The team documented thermal inertia with gentle lamp-level heating and observed a slightly delayed surface response. They logged a precise mass and noted tiny variations across repeated measurements that were too small to declare a trend. They checked for magnetic ordering and found none at room temperature, no stick to a magnet, and bias on a compass needle. They took air samples from the crate in the storage room to see if any off-gassing correlated with the vegetation die-off in Buga. Nothing obvious popped out. Interpretations branched. One group framed the design as communication hardware, a central controller, optical routing, and resonant cavities as modulators. Another looked at it as a control system for managing mechanical stress and vibration, a kind of ultra-refined damping core. A third kept it simple. It's a sculpture built to look like a puzzle. With no seams to open and fasteners to undo, the orb refused the usual engineering playbook. The lab ended its initial phase with an accurate catalog: shells, inclusions, a central dense element, faint exterior markings, and an internal connectivity that looked deliberate. The headline wasn't an answer, it was a layout, an architecture without a manual. Structured signal. The lab's baseline period was supposed to be uneventful. Shielded walls blocked outside interference. Instruments hummed along, logging background noise. Static, low-level vibrations, the usual lab ghosts. Weeks passed without incident until a flicker appeared. It was brief, broadband, and forgettable. A transient so quick most of the team didn't even notice until they scrolled through logs later. The note beside it was casual. Single anomaly, likely interference. Then, weeks later, another flicker. This time, the instruments caught it clean. When researchers lined up the two traces, similarities surfaced. Timing intervals that seemed to match, a waveform with an almost familiar rhythm. One spike might be nothing, two that looked alike. That raised eyebrows. Still, no one declared discovery. Labs have been fooled before. Interference can masquerade as order. Yet the resemblance between the two events pulled the team into long nights of analysis. Autocorrelation tests, the math that checks whether a signal mirrors itself, showed peaks above background noise. Entropy estimates hinted at reduced randomness. Fourier transforms teased out faint tonal features. Each tool suggested there might be more here than chance, but none could close the case. So the debate began. One group called the events diagnostic chatter, like a heartbeat from a machine running quiet checks on itself. Another imagined data broadcast, a payload hidden inside timing gaps. A third argued it was environmental noise in disguise, and the sphere was innocent of all mystery. To push the question, the lab rotated controls. They stepped the room temperature within safe bounds. They added damping pads under racks to blunt vibrations. They cycled nearby electronics, mapped RF noise, and adjusted antenna orientation. Yet through all these changes, the resemblance between the two anomalies held. Not stronger, weaker, just stubbornly there. This persistence gave weight to the idea that the anomalies belonged to the sphere, not the room. But with only two events, no one could say for sure. 2 points don't make a pattern. They make a possibility. Outside the lab, the story traveled faster than caution. A leaked screenshot of overlapping waveforms hit social feeds with captions like, "The sphere speaks again." To the public, the case was closed. A second pulse meant a signal. Inside the lab, the mood was different. Researchers whispered theories but hedged every word. The official notes used careful phrases. Repeat event with correlated features. Encouraging but inconclusive. Even so, tension grew. Some staff stayed late, staring at scrolling graphs, waiting for the data stream to twitch again. They weren't just scientists at that point. They were watchers, holding their breath for a third strike. The ambiguity itself became the story. Was the sphere broadcasting, breathing, or just reflecting our own urge to find meaning in static? The answer hadn't come yet, but the question had lodged deep. What mattered wasn't certainty, it was possibility. Two echoes, in a place where silence should have ruled, had unsettled the room. Enough to stir excitement, enough to feed doubt, enough to keep everyone listening. Whether it was a heartbeat, a beacon, or just an illusion, the so-called second pulse pushed the Buga sphere from curiosity into suspicion. Something had stirred, twice, and the only question that mattered now was this. If it happens again, will we still call it noise? Astral patterns. Long before anyone in Buga stared up at a zigzagging orb, astronomers were cataloging the sky's own repertoire of strange rhythms. Pulsars, rapidly spinning neutron stars, tick like cosmic lighthouses with millisecond-to-second precision. Magnetars throw tantrums. Fast radio bursts flash and vanish, some once, some in sequences that almost but not quite repeat. The wow signal of 1977 remains a one-off mystery that inspires more caution than conclusions. In 2025, 3 results set the tone for how scientists think about repeating energy signatures. First, researchers traced 125.5-minute rhythmic radio pulses to a binary system about 1,600 light-years away, where a white dwarf and a red dwarf interact magnetically. The cadence wasn't communication, it was astrophysics. Fields twisting, plasma snapping, a cycle written by orbits and magnetism. Second, a source dubbed ASCAP J 18320-911 inside our galaxy pulsed roughly every 44 minutes in radio and X-ray bands. Its dual-band behavior didn't match standard pulsar models, forcing new ideas about slow, energetic emitters. Third, observers logged an exceptionally bright FRB from a galaxy approximately 130 million light-years distant, the kind of single powerful event that gives instruments both a stress test and a treasure trove. Against that backdrop, it's natural to ask how any repeating terrestrial pattern should be compared to the skies. The right tools are statistical and cautious. Periodograms reveal dominant cycles. Autocorrelation highlights self-similarity. Wavelet analysis catches structure that changes over time. These methods don't tell you who is speaking. They tell you whether a rhythm exists and how stable it is. Some researchers looking at public discussions drew analogies to double optical pulses reportedly seen from the star HD 89389, closely spaced, repeating features whose cause remains unclear. Whether those specific stellar observations stand the test of peer review is secondary to a broader point. The universe is rich in regularities produced by physics. Rotation, orbit, precession, resonance. Nature repeats when systems lock into cycles. Regularity alone is not evidence of intent. That's not a buzzkill, it's a roadmap. If a pattern here on Earth superficially resembles cosmic behaviors, the comparison can guide tests without importing assumptions. Does the timing drift with temperature the way some mechanical resonances do? Is there a phase relationship to local fields? Does the spectrum show harmonics characteristic of a specific process? Do gaps cluster as if set by a clock or smear like a noisy relaxation? In astronomy, repeaters teach humility. Early FRB discoveries set off waves of "maybe it's a message" headlines. Years later, repeaters and non-repeaters alike began to map onto environments, star-forming regions, magnetized neighborhoods, where extreme physics does the talking. The lesson is that context narrows possibilities. For a terrestrial pattern, context means lab environment, materials, and response to controlled change, not analogies stretched across light years. Still, thinking cosmically has value. It normalizes the idea that structured emissions are not rare in nature. It also improves discipline. Astronomers publish time series, power spectra, and uncertainties. They share raw data and let others reanalyze. Adopting that culture around a terrestrial anomaly makes claims reproducible and falsifiable. If the pattern holds under that kind of scrutiny, consistent timing, stable morphology, clear separation from environmental drivers, then the conversation can move from "it looks like X" to "it behaves like Y under Z conditions." In short, the sky offers both inspiration and guardrails. Rhythms aren't inherently messages, but they always mean something. The task is to find out what without borrowing answers from the stars when the mechanism may be sitting on the workbench. Rational methods. From the beginning, critical voices urged a simple rule: extraordinary claims require ordinary discipline. Dr. Julia Mossbridge, a physicist who has weighed in publicly, framed the object as likely human-made, possibly an art project, and argued that declaring alien before rigorous vetting risks confusing curiosity with conclusion. Her stance isn't cynicism, it's process. Start with the most common explanations and eliminate them methodically. Institutional lessons back the cautious approach. The Pentagon's All-Domain Anomaly Resolution Office has repeatedly stated that cases they investigated show no evidence of extraterrestrial origin. Many resolve into balloons, drones, birds, satellites, and sensor artifacts. NASA's 2023 UAP study reached a similar conclusion. Ambiguous observations often reflect limited data, not exotic physics. None of that means anomalies never exist. It means the base rate for prosaic explanations is high. Skeptics argue that extraordinary claims about artifacts like the Buga object demand rigorous, standardized methods that prioritize data over narrative. First, they call for independent imaging and materials analysis. Multiple labs should run their own X-rays and CT scans, with results compared across facilities. Non-destructive spectroscopic techniques like XRF and Raman should be used to characterize both the material composition and any surface treatments. Discrepancies, such as differing counts of microspheres, must be resolved through shared protocols, not subjective interpretation. Transparency is also essential. All raw data should be released. Time-stamped files, instrument settings, environmental logs, and even the code used to generate any claimed emission patterns or spectral correlations. If a signal is real, others should be able to reproduce it. Environmental controls are another key. Labs should map and document their own RF noise, vibration spectra, grounding setups, and temperature cycles. Repeating tests in different environments can reveal whether anomalies are tied to the object itself or just to the room it's in. Independent review strengthens credibility. Skeptics recommend involving third-party scientific groups, like the Galileo Project or the SCU, to bring in outside expertise and ensure the methodology stands up to scrutiny. Finally, provenance must be airtight. Every transfer of the object should be logged with names, times, locations, and high-resolution images. Storage conditions need to be tracked. If field samples exist, they should be archived. Without this chain of custody, contamination claims become impossible to rule out, and results become impossible to trust. Mossbridge also stresses psychology. Humans are pattern-seeking. We find faces in clouds and messages in noise, especially when the unknown triggers fear or awe. That reaction isn't shameful, it's human, but it is a reason to slow down. If people want this to be a message, they will read one. The antidote is pre-registered protocols and blind analyses that reduce expectation bias. International considerations matter too. The artifact surfaced in Colombia and, according to some reports, has been examined by teams in Mexico. Moving potentially significant objects across borders raises questions. Who authorizes testing? Who owns the results? And how are samples shared? Skeptics argue for non-governmental, non-partisan consortia with published charters to avoid political whiplash and to ensure access for qualified teams regardless of nationality. None of this dismisses wonder, it channels it. A rigorous negative result, it's an artwork with clever internal structure, still teaches something about materials and craft. A rigorous positive result, here is a reproducible, structured emission with defined environmental independence, earns attention precisely because it survived attempts to disprove it. Methods before mystique isn't a buzzkill, it's how unknowns become knowledge. Exotic physics. Speculation filled the gap between scans and certainty. The boldest thread centered on whether advanced engineering could manipulate inertia and gravity directly. Three ideas dominated the fringe-to-frontier spectrum: negative mass, electrogravitics, and fractal space-time topotemporal models. Negative mass is a thought experiment with unsettling consequences. Give a system effective negative inertial mass and push it forward. Its acceleration points backward, like a shopping cart that surges into you when you shove it away. In practice, condensed matter systems can exhibit effective negative mass under constrained conditions, but extending that to bulk, room temperature engineering is a leap. If a device could toggle its effective mass distribution, it might reduce apparent weight by large fractions without expelling reaction mass. An echo of claims that some exotic machines lighten by 80% under operation. The theory demands a mechanism to couple fields to mass energy in a controllable way. No conventional blueprint exists. Electrogravitics, the idea that high electric potentials can induce gravitational effects, has a 20th century paper trail full of patents, anecdotes, and little in the way of controlled, peer-reviewed success. Still, the concept refuses to die because it promises a direct line from voltage to lift. In modern framing, any such effect would likely be a misidentified interaction, ionic wind, corona discharge, or electromagnetic forces on the test rig, unless a clear, repeatable gravity coupling term is isolated. Advocates argue that carefully arranged resonant cavities and layered dielectrics could concentrate fields the way RF cavities concentrate standing waves, producing forces that feel gravity-like. Critics say the math doesn't add up. Fractal spacetime and topo-temporal models go further. They propose that spacetime has scale-dependent structure, roughness that devices could exploit, or networks that map onto geometry at multiple scales. In those pictures, arrays of microspherical cavities and fiber-like networks aren't just signal paths. They're couplers engineered to interact with space-time's texture, redirecting inertia or enabling inertial shielding. One proponent, cited in discussions as Patrick Morsua, sketches a framework in which a nested internal network induces a negative mass effect by routing energy through a fractal metric. It's elegant language without mainstream endorsement. But as a design narrative, it explains why a device might include concentric shells, tuned inclusions, and a central control element. A practical question cuts through the theory. What signatures would such systems produce? If a machine manipulates inertia, it might radiate at specific bands during mass shift transitions. If it couples electromagnetism to gravity, it might produce small but measurable local cooling due to energy partitioning, or show weight fluctuations synchronized with an internal cycle. It might also exhibit extreme thermal management, fast heat rejection or absorption, as a byproduct of field interactions. Testing these possibilities doesn't require belief, it requires disciplined measurement. Vacuum chambers to remove ionic wind, torsion balances isolated from vibration, calorimetry with millikelvin resolution, and broadband sensors that log fields from DC to microwave. There's a social dimension to radical theory. Bold ideas attract bold claims, and the internet rewards certainty. The path forward is to translate metaphors into testable hypotheses. If a negative mass regime exists, then under X stimulus, the apparent weight will change by Y for Z seconds, independent of ambient conditions. Pre-register the plan, run the test, share the data. If the effect isn't there, adjust or drop the model. If something persists across labs, even skeptics will follow. Future governance. Whatever the final verdict on the object, it has already done real work by forcing institutions and communities to organize around uncertainty. The immediate next steps are technical, but the broader agenda is human. How we study, share, and decide. On the bench, the plan looks like this. First, controlled stimuli with long, quiet windows. Modulate temperature in tight logged steps. Introduce calibrated acoustic and mechanical inputs. Sweep electromagnetic fields at low power with known polarization. After each stimulus, record extended baselines to see if any response repeats with the same signature and lag. Second, environment swaps. Repeat measurements in another building, then another city, to prove the phenomenon is attached to the object, not the room. Third, instrument diversity. Redundant sensors from different vendors, synchronized by GPS-disciplined clocks, reduce the odds that a single device's quirk will write the story. Next comes transparency. Publish raw time series, not just plots. Release sensor calibration files, room surveys, and code. Invite independent teams to reanalyze. pre-register test plans so the community can hold researchers to their own standards, and so negative results count as progress rather than silence. This is the normal way to make unknowns legible. Then there's governance. The object was recovered in Colombia. Some testing has reportedly occurred in Mexico. Cross-border handling of unusual artifacts raises issues of cultural property, national security assessments, and scientific access. A credible path is a multinational memorandum of understanding that defines custody, sampling rights, and publication rules in advance. Non-governmental coalitions, think the Galileo Project or similar consortia, can host data repositories and convene review boards with members from multiple countries to blunt accusations of secrecy or capture. Risk management belongs in the same document. If an artifact exhibits uncontrolled emissions or triggers environmental effects, establish thresholds for pausing work and criteria for moving to higher containment. Spell out who makes that call and on what evidence. Align with existing lab safety frameworks, radiation, high field, cryogenic, so teams don't improvise under pressure. Public communication is a parallel track. Regular, boring updates. New scans uploaded, no change in mass measurements, next test scheduled, outperform dramatic pressers in the long run. They prevent information vacuums that conspiracy narratives rush to fill. A single web page with a changelog and data links can anchor the discourse better than 100 interviews. Education is a hidden win. A rigorous case study, how to handle an ambiguous, high-profile object, will teach students statistics, measurement science, and ethics better than any abstract lecture. Schools can build open datasets into curricula, training the next cohort to work with uncertainty without overpromising. If, after all that, nothing extraordinary remains, no stable emissions beyond environmental controls, no reproducible anomalies, the story still matters. It will stand as a demonstration of how to investigate viral claims without mockery or panic. If, on the other hand, a stable, structured effect survives cross-lab scrutiny, the work shifts to engineering, characterize the phenomenon's limits, map its inputs and outputs, and look for applications that are safe and lawful. Transportation, energy, and communications will be the obvious magnets for attention, but rushing there without understanding will repeat old mistakes. Guardrails must move with the ambition. Finally, there's the civic piece. Should we ever answer back to a signal from an unknown device? That decision isn't just technical. It's a question for ethicists, diplomats, and the public, with precedent in debates over messaging extraterrestrial intelligence. A practical stance for now is asymmetric. Listen widely, publish carefully, transmit nothing without broad consensus. Thanks for watching. If this blew your mind, smash like, share your thoughts, and subscribe for more cosmic mysteries. Stay tuned, stay curious, because the universe always has surprises.